Welcome back to another video for AP Physics Mechanics, and we'll be going over work and power and energy. Okay, so getting started. Uh, sorry, getting started. Work is the process of applying a force through a distance to change an object's energy. Okay, and positive work increases V and vice versa. All right. So work comes in three different forms, and you can find work in three different forms. So I wrote them down here. So the first way is work equals FD cos theta, right? Work equals the force times the distance, or the distance, the motion of the object, times cos theta. And if you're wondering what cos theta is, it's usually the angle that the force vector creates and the motion of the object. So let's say an object goes like this, right? And it is moving by a force of F. And the motion is also that way. So the angle in between is 0. So it's FD cos 0. And that's it. And keep in mind the units of work is in Newton meters or joules, okay? Another way to find work is to take the integral of a f of x function, right? So if you're giving a function, it's f versus x, just take the integral of that and you should be fine. Next thing is that when you're given a f versus x graph, work is the net area of that graph. So the area under the curve or whatever, right? So moving on, we also have power. And power is the rate of work, or it can be known as the work done over a time t. So the equation for that is power equals work over t, time. And the units for that is joules over seconds, which is watts. Okay. You can also find power if you just take the derivative of work, right? And you also can do power equals force times velocity times cos theta. Once again, it's the same thing as like the work formula like this. It's scalars, you know. You have to find the angle in between the motion and that. So yeah, it's pretty simple. And moving on, we have different forms of energy, right? We have usually we have kinetic, gravitational, potential, and spring potential, right? And so kinetic energy is the energy possessed by already moving objects, right? As you see by the velocity, okay? And potential energy is the energy possessed by an object based on position, which is gravity and the spring, because position both play a role in these formulas. C, height, and C, the distance that the string compresses or contracts, you know. Another way to find the forms of energy, right? Change of potential energy equals the negative integral of fx dx. And the reason for this is that these come from these are based off of this formula, if you get what I'm saying. I don't really know how to explain that well, but so a gravitational spring, let's say, it comes from the f of x. Hooke's law is negative k of x, and so if you negative integrate this, right, it becomes 1/2 kx squared. That's how you get it. So this is used when the formula given is not negative kx. Let's say it's negative kx squared. Then this would be different completely. So that is just like for those rare cases that the problem changes up the formulas. I don't really see those. I didn't really see any of those that much, but you could have some. So keep that in mind. And another good thing to note is that force equals the negative derivative of potential energy versus x. Okay. And in the end, mechanical energy equals the sum of kinetic and all the potential energies. All right. And mechanical energy is basically like the total energy of a system, which we'll be getting into shortly. And so we have stuff like the work energy theorem. This is a really good thing to memorize. It can help you out in many different ways. So it says that the net work is equal to the change in kinetic energy. The reason for this being so helpful is that kinetic energy has velocity. So if a problem asks you to find the final velocity, it gives you the stuff and the conditions meeting work. It's easily done. Okay, so it's a good thing to note. If a problem arises, then and you don't have like the necessary resources, or if it asks you for finding like velocities or whatever, this is a great formula to use. Okay. And next, we have the law of conservation of energy. So basically, this is that the total energy of an isolated system, it remains constant. Okay, so that means everything's like preserved. And here, I'll show you 4 different cases of isolated systems and what you can do. So if there is like a little diagram, or if the problem describes like it sets up a system, basically I'll refer to it as a system. It sets up a system where there's no external forces acting upon the object, and all the forces are conservative, right? So that means that the total energy taken at one point must equal the total energy at another point. So mechanical energy equals mechanical energy. That's basically what you have to think about. So let me give you 4 different little examples of such, situations. So first you have, like, let's say you have a pendulum, right? The problem says that the pendulum is dropped from position blah 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 and it moves. So basically what I like to do is you set up like a little ME versus equals ME, right? And since you know that mechanical energy is kinetic plus all the potential energies, you just rule out what is there and what is not. So let's say that this side I'm counting for as this position. And let's say the problem says from rest, and some person is holding it and drops it from a position H. Now what you can derive from that is that the conditions for potential energy gravity is met, right? Because it has a height of H from this, right? Kinetic energy, there is none, because the object, remember, is not in motion. It's like initially at rest, okay? And there is no springs, so there is no spring potential energy. Okay, next, you have to set that equal to another point, right? So let's say right here, the mechanical energy for right here. What can you determine from this? Well, the pendulum has lost H. It's at the original position. If you denote this as x equals 0, remember that x equals 0, you usually denote it to the lowest position, right? And that, so when H is lost, there is no potential gravitational, right? There's no spring potential because there is no springs. And so the only thing is kinetic energy. And this makes sense because usually you would assume that when you drop a pendulum from a height of H, it would move, right? There's motion. And it doesn't just stop in time right at this moment. It keeps on flowing, right? It keeps on moving. So kinetic energy is there. And remember, kinetic energy is the energy possessed by moving objects. So basically, what you end up in the end is that you end up with like a little system that you get, right? mgh equals 1/2 mv squared. And from there, you can cross out m because they're the common constant, right? And you solve for whatever you need to solve. Okay? So another example we may have is that an object is pressed onto a spring, right? And the spring, I don't know how to word it, but like it pushes the object and the object moves across the table, right? So once again, a system, think about it. Think about the conditions that are met and think about the conditions that are not met. So for this one, there's no height, there's no h. It is at the lowest point, both of these. So there's no gravitational potential, right? And let's say the problem says the object is pushed onto the spring and kept there for a second or two, right? So the motion right here is still, so there is no kinetic energy. Only thing that's remaining is spring potential energy. So the only thing here is US, right? And let's say the spring explodes, right? Or not explodes, but like pushes the object, let's say. And the point is that the object is in motion at this point right here. And so think about it again. There is no gravitational potential, right? There is no spring potential. The spring potential is only here when there was actually a spring, but this is purely an object in motion, right? There's no spring around it. So the only thing that it is kinetic energy. It is in motion, so thus kinetic energy would be the most rational choice. So basically, you set it up again. 1/2 kx squared equals 1/2 mv squared. And you can cancel these out, 1/2, and you solve for whatever you need to solve. Now, you have something like this. I didn't draw that well, sorry, but you'll see the point. So let's say there's an object, right? There's an object, and it's put onto a spring that's put upwards, right? Vertically. And the spring compresses, and the object stays there for a little bit. And then after a short period of time, the spring, releases, and it pushes the object up into the air. So what are the conditions for this? You have to think about it. For this, you're at the ground. The problem says you're at the ground. The object's at the ground. So the height h is 0. There's no height, right? So gravitational potential does not exist for this point. Moving on, the object, let's say the problem says at rest. At rest meaning there is no motion, and so there is no kinetic energy. Okay? And so the only thing that is left is the spring, and that is spring potential. Okay? And once again, take note of another point, right? It is in motion in the air. So let's say it's not at the peak, but let's say it's just on the way, okay? It's moving, like this. So what you can see from here is that the motion... Wait a minute. Oh, okay. Well, you can do the motion and that'll be kinetic, but in this case I didn't write that out. So let's say it just reaches a peak where velocity equals 0, okay? So it's not in motion, it's still in the air. It is at the terminal height of the trajectory. So the only thing that it is gravitational, because that's h, right? But you can also have k if the problem says it has not reached the terminal height, or it's on its way up, or it's in motion on the way up. You could usually determine, right? So it's 1/2 kx squared equals mgh, and solve for that, yada yada. And something you might encounter is like an object on a spring rolls up a hill after the spring releases, and the object's in motion right here. So once again, determine the conditions: spring potential, gravitational potential plus kinetic energy, and set it up like that. So these 4 situations are like usually common, but there are a lot of different ones. So if you were to take away anything from this little unit or subsection, just take away that just think about it that mechanical energy of a single point has to equal the mechanical energy of another point. So, and this is only for isolated systems, okay? So fulfill the conditions in your mind, like think through it. Does this meet gravitational? Does this meet spring? Does this meet kinetic, right? And once again, let me run through it really quick. Kinetic is energy possessed by moving objects. Gravitational is when an object is placed above a height h, at a height h, and spring potential is just when there's strings. Okay, so that's that. And keep in mind that energy can transform slash transfer slash leave slash enter systems. Okay, just keep that in mind. And sometimes the problem is like calculate, let's say, the loss of energy or calculate the gain in energy. And so what you have to do is basically solving for the loss of energy, you just set let's say in this case you just set gravitational potential minus kinetic, and it calculates the loss in kinetic energy in heat, in the form of heat, you know. So the total energy at one point cannot equal the total energy at another point. Some of the energy is lost in heat, so you can solve for that heat by setting that system but subtracting those. Okay, and I think that is all. So yeah, okay, yeah, that's it. And this was work, energy, and power. It was pretty short, since you can tell. The reason for it being so short is that it's pretty easy. It's pretty easy to wrap your head around. There's no kinetic energy, potential energies, mechanical energies, isolated systems, work, power, all that. So yeah, that's pretty good. Thank you for watching the video. Maybe I'll probably do my best to release another video soon. I don't know what it's gonna be about. Probably something about momentum and impulse. And so thank you for watching. Stay safe, everyone. Wash your hands, wear a mask, and I'll see you next time. Okay, have a good one.